Hey there, this is John with gringo.dev. I wanted to do a quick video talking about time series data and options for handling it. So this is something that I have been investigating for my personal reasons recently for a project that I'm working on, where we're going to be handling large amounts of time series data. And so given that I had to do this research anyway, I thought I would share it with all of you guys and talk through a bunch of options, different trade-offs, things like that, things to consider depending on the characteristics of the application that you were trying to build. And so the first thing to talk about is what is time series data exactly? And so it's probably easiest to think about it through examples. And one example that you could think about is something like a loan company. So if you're doing, let's say, micro lending with people, maybe you have a large amount of applications coming in every day. Probably you have a machine learning model somewhere that actually, I hope you do, that fairly and without bias classifies people according to risk and ultimately returns a decision that says they are approved or they aren't approved or we need more information or something. And so you might represent that with a simple schema. We'll call it loan decisions. And in that schema, you'd have an ID, probably a user ID. You'd have the decision itself in whatever way you want to represent that. And then you would have a timestamp. And so that's where things get interesting, right? So with time series data, you're essentially talking about events more so than you were talking about records. And so that's a little bit of a mental shift. And so we'll get into this more in a bit, right? But one of the characteristics of time series data is that it tends to be more columnar in nature. You are more concerned about the columns and the aggregations on those columns than you are about the individual rows, at least in this context. You might use the same table for two things, like one to power for example, in this context, you might have a website that says your loan was approved, and you would pull directly from the table the normal way using the row. But for the purposes of presenting a dashboard to the CEO or an analyst or something like that, you'd be much more interested in how many loans did we approve today versus how many did we deny. And so that's the essence of the difference. And these sorts of problems tend to have different characteristics, right? So the first thing to think about, I kind of mentioned the columnar versus row thing. But just to illustrate that a little bit, in a normal like row-based storage system, you would have something like this, right? So the ID might be 1, the user ID might be 1, the decision might be approved, and the timestamp would be what have you, right? And then you would have another row that might be 2, 2, denied, like that. Now, in a columnar system, you would store things by column, right? So you would have your, let's see, ID column. That would be 1 and 2. You would have your user ID column, which again would be 1 and 2. You would have your decision column, which would be approved, denied, and then you would have your timestamp column. And so you can see here there are already some interesting characteristics. And just to be clear, you don't necessarily have to switch to a columnar storage system. It's just a way of thinking about it. But we'll talk more about that later. But the basic idea here is that you can see these things tend to be append only. So you have a series of events. That list of events is only going to get larger. And you also are mostly interested in counting, averaging, summing, like some operations on these columns. The other thing that's interesting about them is that at least if you were storing things this way in a columnar format, you're going to get what amounts to inherently an index. So if you were to create an index on a table, it would actually end up looking a lot like this, with a series of IDs, a series of user IDs, decisions, and so on. And so we're going to come back to that in a bit, like I said, but just things to think about. The other thing to consider is that this data tends to be rather large. Again, it's append only. The list grows as you have more events. And because of that, I'm kind of skipping ahead a little bit, but you end up doing sequential scans a lot if you are not careful. And so if you have to visit 10,000 rows to do your aggregation, you have to visit 10,000 rows. If it's 100,000 because you had a good year, you're going to have to visit 100,000 and so on, right? And so these strategies are mostly oriented around the idea of minimizing the number of visits you have to make to the base table, such that your aggregations can be efficient, or at least efficient enough for the purpose that you have in mind. And so that's actually a good point too, right? So the use case matters a lot. And that's something to think about for the purposes of whatever you are building. So one distinct use case is call it your OLAP. And OLAP is just your analytics, your dashboards, things like that, right? And so you first need to decide like what time horizon do I care about for the purposes of creating a dashboard? Who is my customer? In this case, it's likely to be internal, things of that nature. And so, the one thing I would probably caution against here, by the way, is, if possible, avoid real time data. And that's for a couple of reasons. One is because real time analytics are actually kind of hard to do and support and operationalize. And I also just kind of question how useful they are. So I worked at a previous company, a large one actually, and I'm kind of guilty of this, by the way. So I kind of prototyped the initial version of this real-time metrics dashboard myself, and the executive team liked it so much that they turned it into an internal product, which I soon came to regret because, practically every morning I would get a panicked email from somebody saying that the numbers didn't smell right. And almost invariably, when we looked into it, it was not actually a problem. It was quite literally either noise in the data or the reporting itself had gone out for like maybe 30 minutes and the numbers looked artificially low until they had caught up later in the day. And it was a giant distraction. So, unless you just need the real time case for some reason, for both business reasons and also just practical implementation reasons, it's probably best to avoid it. But the refresh rate, like the time horizon of your data, is an important consideration here. And in some cases, you might end up with OLTP as well, meaning stuff that you have to display to actual end users somewhere. And so the same considerations apply around figuring out the refresh interval and like all of these things. But also you have the other things that matter as far as hardening and monitoring and like all of that stuff that goes with actually displaying data to the outside world. So keep all of that in mind. And, some of these recommendations will apply more to one use case than another. But going back to the example that we have up here, so we have a loan decisions table. And so, of course, it's just a sequential entry that gets updated, or more precisely appended, every time we have a new decision, right? And so, of course, that table can grow arbitrarily long. And, let's say that you want to build a dashboard that does something very basic, right? So in this case, the problem is give me a breakdown of decision type by time. And so that might actually be as simple, at least in principle, as something like, um, select count ID from loan decisions, and you're going to group by the decision itself. This is my anal retentive nature coming up. And then, yeah, group by decision. And then you would probably group by the timestamp as well if you want to break it down by like hour, week, day, month, what have you. And so that would be a very basic way to do something like this, to create an aggregation on top of this data. But like I mentioned, the problem with doing something like this, at least naively, is that you are going to end up with what amounts to an O of n problem, where you have to do a linear sequential search through the database to find all of these records and then calculate your counts on them, potentially every single time that you want to do the aggregation, right? And so there's a few options to deal with this. I think my preference, if you don't have a reason to do something more sophisticated, would be to basically take this query right here, and then you have some options, right? So you can probably, like, the low-hanging fruit is going to be something like this plus some indexes. So you could just add an index to decision and ID, and all of a sudden you've basically solved your sequential scan problem, because you'll have actually something that looks more like this or more like this, as opposed to having to visit every single row. And so if you needed to do a count of the type of decision here, if you already have an index, which again, I was illustrating this as part of columnar storage, but the index looks very similar. Instead of having to go through every row, you can actually just operate on this column. Like, that's essentially the transformation that gets made. And so then if you wanted to do a count of each type, you're actually not having to visit a whole lot of places to do that calculation. And this can work very, very effectively, especially if you don't need a whole lot of indexes. And so just as a rule of thumb, by the way, I mean, you don't want to go nuts with your indexes, but in cases like this, where you know that you're going to have to filter or aggregate on a column, that's probably a good reason to put an index on it. You don't want to go crazy because there's actually a cost associated with creating indexes. It'll make your write performance slow or slower. just objectively. That is fundamentally the trade-off, but it will make your reads on those columns, especially if they're all contained in an index, much, much faster. And that can be incredibly powerful for a case like this. So that would be some very low-hanging fruit. And in the case where, let's imagine that this is a dashboard that you're actually exposing to an end user somewhere, and you want to avoid the case where they're hammering the service all the time, all this stuff. If you can get away with a little bit of stale data, just throwing a Redis cache around this with an appropriate cache time can actually be very effective. So you can imagine, like, to the point that I was making earlier, like real-time data is actually a lot more valuable in theory than it is in practice. So even if you just make an SLA with your end user, whoever it is, that we only refresh our data once per hour or once per day or something like that, between this, and this, you can probably get pretty far. And then maybe you just have a batch job or something that can update that. I mean, there's some different options that you can take from there. So another option here that's a little bit more advanced is what's called a materialized view. And a materialized view is essentially just you can almost think of it as a cached SQL query. But that becomes essentially an artificial table. And so you can imagine the same query that we have up here. I'm not going to write out the whole thing, but this becomes your subquery or your CTE. And then you would call create materialized view using that. And you could call it like loan decision aggregation or summary or whatever you want. And then effectively you have a table that represents all of the aggregations that you're interested in. And so that can be a very convenient way to represent these types of problems because you'll already have what you need to create the dashboards that you want to create. So the only real gotchas here are that the materialized views, at least in Postgres, are not refreshed by default. And so what that's going to have to mean is that you take on some operations burden. And that's going to be something like a batch job or something like that that can come through and recreate that materialized view with fresh data on whatever interval makes sense for you. And so you're going to have the normal sort of batch job problems that come along with that, which is, I think there's a technical term for this, but it's escaping me. But the basic idea is that you want to make sure that the time to complete the job is ideally much less than the refresh interval. And, obviously if it takes like a day to compute these new numbers and refresh the view, then that's going to be a problem if you have communicated a 1-day SLA to your customers. And so that's just something that you would have to think about, monitor, like all of those things. It's probably not a huge deal, but yeah, it is something to think about. Um, So another option that is worth considering is TimescaleDB. And so TimescaleDB is an extension for Postgres specifically, and it actually does a lot of very cool things for you. Things like continuous aggregations. And so what I mean by a continuous aggregation is that Timescale creates what's called a hypertable. And so you can sort of, to the point earlier about columnar versus row storage, what it is essentially doing is it is partitioning your data, like dividing it between a bunch of subtables, but more or less transparently to you. And it realigns your row-based schema to be columnar for faster querying, aggregations, things like that. It does a bunch of sophisticated compression on your data, and you get a maybe not instant, but very fast refresh time, as opposed to having to do more of a batch and refresh a materialized view. So you could almost think of a TimescaleDB as being materialized views with a few bells and whistles. Right, so we're actually going to jump over to Timescale's website and just check out some of what they talk about there. All right, and here we are. So if you go to timescale.com, you can find more information about the project. They have some pretty good documentation here. There's some tutorials oriented around different use cases and things like that. I'm going to kind of zoom in on a particular part of the documentation that talks about continuous aggregates, because that's what's most interesting to me at the moment. But yeah, you can actually see, like I was saying, that TimescaleDB quite literally is Postgres materialized views, but with some bells and whistles. And so actually step one in creating a continuous aggregate in Timescale is to create a materialized view. And I believe by default it actually does update, but you control exactly the interval that you want things to update at. So that's done with this time bucket SQL function that comes from timescale itself. And that's actually pretty much all you have to do. So what's going to happen is you set this up, you deploy it as an extension in Postgres, and then as sort of a periodic background thing, your materialized view is going to be updated with the most recent data, the aggregations that you set up on your columns, etc. Right? So you could imagine, like to my earlier schema, the example one, there were decisions, right? So you could imagine that instead of doing average, max, min, it might be just a count broken down by decision. And, I can control whatever I want the aggregation frequency to be. So you can imagine in the case of a dashboard, I might want to be looking at day over day, week over week, month over month type metrics. And so having those just essentially cached in a materialized view, but something that I can just very easily query, the whole process of aggregating this stuff inside the table, handling the refresh, all of that is very conveniently abstracted away from me as the developer. And so that makes things very easy. And as far as like operationalizing this, they also have a Docker image that you could deploy to like any Docker compatible host, presumably. So I actually use this one personally on Railway at the moment. It should be compatible with Fly.io or really just anywhere you can put a Docker image. I think this would work. And it doesn't have just timescale, it has PG Vector and a bunch of other extensions that you would want. And so getting extensions to work in Postgres is, not that hard, but, it can be a little bit tricky if you don't know how to do it. So yeah, it's nicely taken care of for you in this Docker image, and, you're pretty much good to go. And so like the only other thing that's worth mentioning about timescale is there has been some pushback as far as the whole like open source branding. Like the source actually is completely open and you can go review it. And they did update their policies recently to allow you to make your own changes and operate a private fork privately if you want to. My understanding, and not a lawyer, not an expert, anything like that, is that the license essentially says that if you are Amazon or DigitalOcean or somebody who might be trying to resell Timescale as a hosted offering, because they do have their own hosted offering, you're not required to use it, but they do, then I believe that's prohibited or requires a payment or something like that. But I think the way they defined it in the language was something like if you have a value added service on top of Timescale, in other words, you're building dashboards on top of it or something like any number of use cases we talked about in this video, you're completely fine. And that's actually permitted and free forever. And the source is available and all of those things. So for me, anyway, like I tend to be fairly pragmatic about these things. And the distinction between source available versus open source is not particularly meaningful for me. And I have no ambitions of creating an AWS competitor or anything like that. So, from my perspective, it's not worth worrying about, but maybe your needs are different. I don't know. So anyway, in my experience so far, I've been very impressed with what they're up to. And just to be clear, I'm not sponsored or anything. I don't accept sponsorships at all on this channel. But yeah, if you're really interested in doing some time series analysis and something a little bit more sophisticated, it's one of those things where it really isn't that much harder than doing a materialized view, and it has some very nice performance characteristics that could help you out a lot, and just avoid having to think about this problem for quite a while. So anyway, I hope that was helpful. Just wanted to summarize some findings from my own recent research and implementation. And if anybody is curious, I actually did just end up going with TimescaleDB because I thought we were going to be at the scale where we needed it sooner than later, and it just made sense. But you have any thoughts, questions, criticisms, what have you, please leave a comment, and I always appreciate a like and subscribe as well. So anyway, have a nice afternoon. I'll see you guys soon.